everybody. Our next speaker is Adamaszek from University of Copenhagen in Denmark.
Thanks. I'll talk about submodular unsplittable flow on trees. It's a joint work with Alina and Parinia, who are here at the workshop, and also with Andreas Wiese. So let's start with the definition of the problem. In the unsplittable flow on tree problem, we are given an undirected tree with capacities on the edges, and we're given a collection of tasks. For every task, we have a start vertex and an end vertex, meaning that a task corresponds to some path in the tree, and then we're given a demand and profit. And a feasible solution is a subset of tasks that can be simultaneously routed in the tree. That is, if we look at any edge in the tree, if we look at all the chosen tasks that are using these edges, then their total demand does not exceed the capacity of the edge. And the goal is to find a feasible solution maximizing the profit. And we can generalize this problem to a submodular unsplittable flow on trees when instead of linear profit function, we have submodular objective function. So for any subset of tasks, the submodular function tells us what is the profit of executing exactly those tasks. And just a reminder for people who haven't been here at the previous talk, a function is submodular if it satisfies the following inequality for every two sets A and B. F of A plus F of B is at least F A intersection B plus F A union B. And we assume that the function is given as a value oracle. That is, we can ask what is the value of the function for a given subset, and we get the answer. And the problem is NP-hard already when the profits are linear, and therefore most of research focuses on approximation algorithms. And also another reminder, an alpha approximation algorithm is an algorithm that runs in polynomial time and always outputs us a solution which is within the alpha factor of the optimal solution. Here are the previous results. So when we have linear objective, when our tree is just a path, we have constant factor approximation. And with linear objective for arbitrary tree, we have log square n approximation. When we have a submodular objective, we have log n approximation for a path. And that's our result. For a tree with path with k, we have k log n approximation for submodular UFP, where n is the number of vertices of the tree. And because every tree has path width at most log n, that gives us log square n approximation for arbitrary trees, which matches the same result for linear objective functions. And I'm not sure how many of you know what path width is. So for those of you who don't know what path width is, just think of k as being log n, as it's not crucial for the talk. So essentially, if someone knows what is tree width, so path width is like tree width where you require the tree to be a path. For those of you who don't know what tree width is, just think of it as being log n.
Excuse me, one thing. For the path case, so k equal to 1, for linear objective functions, the best known is better than that. It's log n over log n.
Okay, thanks.
But that's the only case. It's slightly better.
Okay.
And for
linear.
General graphs, is there
for linear is better.
For general graph, like beyond trees and paths?
For general graphs, I think there's very little known. So.
Oh yeah.
So the bounds are much worse. Okay, so that's the high-level idea of our approach. So we will start with an algorithm for linear objective and polynomially bounded capacities. And this algorithm will consist of a few steps. First, we will reduce our problem to intersecting instances. And an intersecting instance is an instance where all the paths go through the root of the tree. And that's a standard step which has been done before. And now we will assume that we have an intersecting instance, and we will partition our tree into a collection of paths. And then for every path, we will consider a geometric viewpoint. That is, not only we will care about the fact that all the tasks have to be routed via the path, but also every task will be considered as a rectangle of where the height of the rectangle is the demand. And then we will want to find a drawing of all the tasks which will be routed via the given path. So that will add some additional constraints to our problem. And then with these additional constraints, we will write an LP. And then we will round this LP using randomized rounding with alteration. That will give us an algorithm for linear objective and for polynomially bounded capacities. Later, we will show how to remove the restriction that the capacities are polynomially bounded. Essentially, instead of allowing arbitrary to draw the rectangles in arbitrary places, we will allow only to draw rectangles as a limited number of places. And then we will show how to extend it to submodular objective function using contention resolution scheme. OK, so we start with something easy with an intersecting instance. So there's the following lemma saying that when we lose a factor log n within the approximation factor, we can assume that all the tasks are crossing the root of the tree. That is, that we have an intersecting instance. And this holds also when the objective function, that is the profit, is subadditive, not only linear. So it holds also for submodular cost functions. And the proof is very easy, so I'll just show it now. We will partition the task into logarithmic number of sets such that each set is a collection of independent intersecting instances. That's our tree, and in the first step, we choose the center of the tree. That is such vertex that in every subtree here will have at most half of the vertices. And our first instance will be all the tasks that use the center of the tree. And that's clearly an intersecting instance. And now we know that none of the tasks are using the gray edges here. So now we have two independent subtrees, and again, for any of them, we choose the center. Again, we choose all the tasks that cross one of the centers. That gives us the second instance, and so on. After a logarithmic number of steps, everything has been partitioned. And here we have a logarithmic number of subproblems. Every subproblem consists of a collection of independent intersecting instances. We solve all of them, we take the best one. So that will lose log n in the approximation factor. So now to the end of the talk, we will assume that our instance is intersecting. And now we will partition the tree into paths. So let us define an upward path. In a rooted tree, we say that a path is upward if one of the endpoints of the path is an ancestor of the other endpoint. So that's an example. We have a tree, and every color corresponds to a path. And you can see that every path is an upward path. And we define a collection of paths in a tree to be a k-nice splitting if every path is an upward path. The paths partition the edges of the tree, and when we look at any leaf of the tree and the path going from the leaf to the root, it uses the edges of at most k paths. So you can see that in the figure here, we have a two-nice splitting, because no matter which path we take into account, it uses at most two colors. And we can show the following lemma, that when we have a tree of path with k, then in polynomial time, we can construct an O of k nice splitting for the tree. And the way we do it is as follows. We start with the edges going down to the roots, and then we assign each of them a unique color. That is, we start a unique path there. And then we proceed bottom up. When we process an edge such that all the children have been colored, we just assign such a color that will minimize the number of colors from the top vertex of the edge to all the leaves. So here at the left, it doesn't matter for now whether we choose red or green. And here also the color doesn't matter yet. And for example, when we color now this edge, you can see that it is best to color it with color purple, as then all the paths will use at most two colors. And if instead we colored with color blue, we would have a path with three colors. So we continue, and we get our k-nice splitting.
How many colors do you need?
At most O of path width. So essentially O of log k, log n.
For a tree.
Yeah. Okay, maybe I won't go into any more details there, but after thinking about it for a short while, I think it's like an easy exercise to try to find out that always log n colors are enough for the tree. And in like binary tree of height log n, you will need log n colors. Okay, so now I will introduce the geometric viewpoint. So now we have the rooted tree, and we have the partition of the edges into upward paths. And now for each path, we can think of it as an independent instance of the problem, where we project all the tasks just on the one path. So for every task, we look at which edges of this particular path our task is using, and that's our projection. And it is easy to observe that if all the tasks are using the root of the tree, and if all the paths are upward paths, it means that all the paths are using the topmost edge. All the tasks are using the topmost edge of the path. And therefore, without loss of generality, we can assume that the edge capacities on the path are non-increasing, because if a task starts somewhere here, it goes all the way to the top. The top now is on the left of the picture. So we can assume that when we draw the capacity profile, it will be a one-sided staircase. Okay, and now we will consider our tasks, and we will draw them as rectangles below the capacity profile. So essentially, for every task which uses some edges of the path, we will draw a rectangle where the height of the rectangle is just the demand of the task, and the length here will be exactly the edges of the path that the task is using. So every task will correspond to a rectangle which starts at the very left and continues somewhere. And then it is easy to observe that any feasible subset of the task has a representing drawing. That is, we can draw the rectangles underneath the capacity profile so that no two of them are overlapping. And the way we do it, we just start with the task that is longest, we draw it at the bottom, and then on the top of it we keep drawing the tasks. And I think from this drawing it's clear to see that if we have a feasible solution, it will never exceed the capacity of the edges. So now based on this, we will write an LP. So we have our tree, we have an O of k nice splitting, and in the IP, we will enforce that for every path there's a representing drawing. So these are our variables. For each task I, we have a variable xi, which is 1 if and only if the task is in the solution. And then if the task is in the solution, then for every path which this task is using, we have to draw it at a certain height. So for each path of our splitting, for each task I, which is present on this path, and for each height, for which if we draw this task at height h will not go beyond the capacity profile, we put a variable y ihp, which is 1 if exactly the task corresponding the task I at path p is drawn exactly at height h. And that's how our LP looks like. Okay, first we have the IP. That's how our IP looks like. We want to maximize the profit of our tasks that have been scheduled. For now, we have linear cost function. Later, I will tell you how to extend it to submodular. And here we have the constraint saying that if a task has been scheduled, then for every path, it has been drawn somewhere. That is, for every path and for every task, the sum over all heights where the task can be drawn of the variables y equals xi. Okay? That means that every task that has been scheduled is drawn somewhere. And the other inequality tells us that the corresponding rectangles are non-overlapping. That is, for every path and for every height, there's at most one rectangle which is active at this height, which gives us this following inequality. And now we will relax it and get an LP. Now our variables xi and our variables y can be between 0 and 1. And we can round it in the following way. In the selection phase, we will pick a subset of tasks and determine a drawing for them. This will give us a solution which is integral but might be infeasible. And then in the second step will be alternation phase. We will pick a subset of the selected tasks such that the corresponding rectangles do not overlap. So how do we do this? In the first step is the selection phase, where remember that we want an integral solution which might be infeasible. So here we fix a large constant C1, and for each task, we add the task to the collection of selected tasks independently at random with probability xi over C1k. So now S will be the set of selected tasks. So now if we selected the task, we also need to select a place to draw them. So now for every task that has been selected, for every path such that the task is active at this path, we need to choose the height. And again, we do the simplest thing. We just choose the height independently at random according to the probability distribution of the variables y from the LP. And that gives us a solution which might be infeasible because, of course, maybe we chose some rectangles which overlap. So now we have the second phase, which is alteration. And here from the subset of selected tasks, we will choose some tasks which will be accepted. And when we accept tasks, we will ensure that there will be no overlapping between the corresponding rectangles. So we will consider the paths in arbitrary order. And for each path, we look at the collection of selected tasks which are active at this path. And then we want to choose a set of accepted tasks such that they don't overlap on this one path P. How do we do this? We order the tasks in non-increasing order according to their demands. So the tallest rectangles first, and then we consider the tasks. And when we consider the task, we already have a fixed height where we can add this task. It's only one particular height. So what we do is we just add this rectangle if it doesn't overlap any other rectangle which has previously been added. If it would overlap, we don't add it. And that's how we decide whether the task is accepted on one particular path. And then our accepted tasks will be the tasks that have been accepted for all the paths. And we can show the following. We can show that every selected task is rejected with probability at most 1/2. How do we show it? So first we show that for any path P and for any task I, which is active at this path, the probability that the task is not accepted if it has been selected is small. How do we show it? That's quite easy because we have ordered the tasks from the tallest task to the least tall task. So whenever we add a task, then if it overlaps some task which has been added before, then either its left top corner must overlap this task, or its left bottom corner must overlap the task, because all the tasks that have been added before are taller. And probability of this happening is small because in our LP we had the constraint that about how many tasks we can add which overlap one particular point. So because everything has been scaled down by a factor 1 over C1k, that's essentially the probability that a task will not be accepted. And now, because every task is active at most k paths, that gives us the lemma that is each selected task is rejected with probability at most 1/2. And that gives us a k-log n approximation algorithm if we have linear objective functions and if we have polynomially bounded edge capacities. Okay, so first I will tell you just shortly how to remove restriction on edge capacities. So the problem is that if we can have exponential edge capacities, then we have exponential number of variables. Because then it could happen that, so then every task can be drawn. We have like exponential number of choices of heights where the task can be drawn. But we can show here that if we restrict ourselves to some carefully chosen polynomial set of heights, then we still get a solution which will only be by a constant fraction worse from the optimal solution. And here I don't want to go into the details. It's quite technical. So essentially, we only choose a polynomial number of heights, and then we say that there's a kind of close to optimal solution, which only puts the rectangles at the given heights. Okay, so now our last part, submodular objective functions. So now I will introduce some notation. Most of this has been present at the previous lecture. So we have a finite ground set N, which you can think of as our tasks. Then we have a family of subsets, which we call I. You can think of it as the integral solutions. And then we have a convex relaxation. We have a polytope Pi, which is a converse relaxation for the constraints. And we can think of the polytope as fractional solutions. And now it's easy to see that the polytope is down monotone. That is, if we have one solution which is feasible, and then we decrease some coordinates from the solution, then also we will get a feasible solution, because we want to schedule less. And then we can see also that the polytope is solvable. It's like a collection of linear constraints, and we can optimize linear functions over the polytope. And then we introduce taking a random sample. So we have some fractional solution x, and a random sample R of x is essentially what was at the lecture before. So for every item, for every task, we take it to the random sample independently at random with probability xi. And then we have multilinear extension that has also been defined before. We have the submodular objective function, which is defined on the integral points, and we want to extend it so that it's defined on the whole polytope, Pi, and on the whole hypercube 0, 1 to the nth. And we defined it by taking the expected value of the submodular objective function on the random sample. So the formula here is slightly different, but that's exactly what is said, the same as what has been defined previously. And now we defined a contention resolution scheme for some constant B and C. A BC balanced contention resolution scheme is a procedure that for every fractional solution, which is taken from the polytope Pi and rounded down by a factor of B, and for any subset A, it returns a random set satisfying the following. The first condition says that with probability 1, this set will be a feasible integral solution. And also, for all the tasks, the probability that a task has been selected to our random set, if it is in the random sample, is at least C. Where here the probability is over both taking the random sample and then taking the subset Pi from the random sample. And we can just observe that we already have the balanced contention resolution scheme. It's exactly our LP rounding algorithm. Because in the selection phase, we took a random sample of this, and in the alternation phase, every task that has been selected is accepted with probability at least 1/2. So that gives us a balanced contention resolution scheme with such parameters. Okay. I don't know if it's clear or. Okay, so essentially our LP rounding just gives us for free the contention resolution scheme. Because first we do selection and then we do alternation. That's the two parameters which we get. And then there's a theorem by Czekuri, Wondrak, and Zenklusen saying that if we have a submodular function and if we have a family of feasible solutions and we have a polytope which is down monotone and solvable, and if we have a BC balance contention resolution scheme, then there's a polynomial time randomized algorithm that constructs a solution which is feasible such that the expected value of the solution is at most theta of the parameters BC times the maximum value of the multilinear extension within the polytope. So what do we get here? We know that we have the balanced contention resolution scheme. We know that the maximum of this function f is of the order of opt. How do we get it? Because if we have polynomially bounded edge capacities, then the optimal solution belongs to the polytope. So this value is at least as large as the maximum integral value, that is, it's at least optimum. And if we don't have polynomially bounded property, then we have shown that still the optimal integral solution here, that within the polytope we still have a solution which is only by a constant fraction worse than the optimal solution. So we know that this value is at least of the order of opt. And that gives us a k log n approximation k approximation for intersecting instances, which gives us k log n approximation for arbitrary instances. Okay, thanks.
So questions?
Can you get any improvement the LP for the unweighted problem? What do you get? Suppose I just want to know how good is the LP for the...
For the unweighted, meaning that the profit is just like linear function summing the number of tasks.
I know that for the path problem that it's constant, but we don't know the integrality gap for the weighted, even in the linear case.
Okay.
It's like most log n, but...
Yeah, I mean, here one thing which we will definitely lose is at the beginning, before we even run the LP, we have to partition our instance into intersecting instances. So that's essentially where we just lose log n at the beginning.
But for intersecting instances, do you...
For intersecting instances...
Or is it...
Yeah, I think here in this setting, I think we will lose k. Because a task can be active on k paths, and then we essentially do independently at each path. So I think here we will lose k. I would have to think if we can do something smarter in this case.
So for the path case,
for the path, yeah.
There's most log n, but it might be a constant.
But unweighted, it is only constant.
The gap.
I mean, depends on the LP, of course.
The rectangle. No, but maybe you don't need to lose a log n for the...
So for the intersecting instances, when we have a path, then k equals 1. Because a path has path with 1.
Yeah, sure. But for the unweighted, you don't lose anything.
Yeah.
Right? You don't need to use intersecting instances.
Yeah, I think for unweighted, for now, this approach doesn't give us anything better, but I don't know if it can be modified somehow.
Okay, let's thank the speaker.